Hello everyone, my name is Jamal Abou and I'm a PhD student in chemical engineering at McGill University. Today I'm so excited to share with you some work that has been done in my master at University of Ottawa as well as ongoing projects in my PhD. The topic is titled First Principles Application of the Geiger Criteria and Heat Pulse Simulation for Phonon Hydrodynamics in Fluorides and Alkali Hydrides. Before I begin, I would like to acknowledge my colleagues and contributors to this work, Dr. Shang Zhang, and my supervisor, Professor Samuel Huberman. I would like also to thank the organizers to give me this opportunity to share our research with you. Phonon hydrodynamics is an exotic phonon transport phenomena. Signature of phonon hydrodynamics is called second sound, which was observed in superfluids like helium-2 and in a handful of materials like sodium fluoride, bismuth, and other materials. The earliest second sound observation was in liquid helium at a low temperature of 2.17. This is also called the lambda point. For fluorides like sodium fluoride, second sound was observed between around 10 and 20 Kelvin, depending on what's called the characteristic length of the material. In this figure, for example, the characteristic length is 8.3 mm of a pure crystal. For bismuth, it was found between 1.2 and 4 Kelvin, also depending on the characteristic length. Theoretically, there are some methods and techniques to estimate phonon hydrodynamics window. Geiger's condition states that phonon hydrodynamics can be observed if average boundary scattering rate is greater than average Ohm scattering rate but less than average normal scattering rate at a given temperature and characteristic length. The highlighted area here shows the hydrodynamic window of bismuth in different characteristic lengths. We can see also here at a certain characteristic length there are different hydrodynamics windows based on the resistive value. So here we can replace U by R since the R is the sum of Ohm and isotopes. We use an APS framework to study phonon hydrodynamics in crystals. There are lots of details, just briefly. So we visualize the structure of the crystal. By using the Phonon calculation, we find the interatomic force constants, and then these interatomic force constants are input to PTE. We solve the PTE and find the phonon scattering rates. And finally, we take the average phonon scattering rates to apply Geiger condition. I encourage all researchers who are interested in this field to read my thesis. So we explain this workflow in detail and we found very accurate results in comparison with the experiments. So we did our calculations at 8.3 mm for a pure sodium fluoride, and we found, for example, at 15 Kelvin we found this temperature in the hydrodynamic window, and this is as found in the experiment. We did our calculations at different characteristic lengths for these for diatomic fluorides and alkali hydrides to show the three regimes: ballistic, hydrodynamics, and diffusive. These four materials are sodium fluoride, lithium fluoride, lithium hydride, and sodium hydride. And we found that the hydrodynamic regime can be found clearly, as you can see from the pink area, between 10 and 80 Kelvin of temperature and 100 and 100 million nanometer of the characteristic length. Second, we have transient thermal grating, TTG. TTG is a useful technique to measure thermal properties of a material, and it can observe the second sound. Experimentally, as you can see here, TTG involves crossing two short laser pulses on a sample surface to create a sinusoidal heat source. And we have here example for graphite. So here we have a comparison between the experimental and theoretical, and we can see that the second sound was found above 100 Kelvin, and also recently it was found above 200. And this is because the graphite has a strong normal scattering in comparison with other materials. Theoretically, we use a numerical solver that was made by Shang. So he uses the Calway approximation to describe the transient heat propagation, and he solved it by discrete ordinate method. So to solve this equation, basically, so there are two steps. The first step is the implicit scheme and iterative scheme. And we can see here that delta t is the time step and is given by this relation. CFL is Courant Friedrichs Lewis number. Delta x is the minimum discretized cell size, and Vmax is the maximum group velocity. And this CFL usually between 0.04 and 0.4. So I really encourage to read more details in this paper. From this figure, we can see by using this solver, now we can describe these regimes, the diffusive, ballistic, and hydrodynamic, easily. So now we can use this numerical solver in these four materials that we have and compare the results with what we found in the Gars condition. So we can see a good sign of the second sound in these three materials, the sodium fluoride, lithium fluoride, and lithium hydride, at 15 Kelvin and 8.3 millimeter. However, we didn't find a second sound in sodium hydride at these conditions. And this is also as we found in the Gars conditions. So we found a good match between TTG and Gars condition. And we can also take any value in the hydrodynamic area. So this is the sodium hydride from the Gars condition. And we can take, for example, at 50 micron and 15 Kelvin, this value, if we use it in TTG, now we can see the signal starts to show up. And this is a good indication for the second sound. And of course, we can use any value, not even this value, but we can use any value in this area and test it in TTG. Finally, we have the heat pulse. Heat pulse also can be used to detect the second sound. This setup is an example of sodium fluoride second sound experiment. By applying the heat pulse experiment, the relation between the arrival time and pulse height can be determined. Here we have two examples at 7.9 millimeter characteristic length for a pure crystal, and at 8.3 millimeter for a very pure crystal. And we can see here there are three waves. The fastest one is the longitudinal sound wave, and the second one is the transverse sound wave, and the last one is basically the second sound. We can see, for example, at 11 Kelvin there is no second sound, only at these two temperatures at this characteristic length. In comparison, for a very pure crystal, we have only two waves. And we can see also this shift between these two waves due to the ballistic phonon relation. So we will use for a very pure crystal to compare with our calculations. So here we use the same simulation that we used in TTG, and now we apply also boundaries. So we add Gaussian heat source on one side with a constant amplitude, and we can see this comparison between the theoretical and experimental at 12.5 Kelvin and at 15 Kelvin. We can see these pulses are in good agreement with experiment, except we can see there is time shift between the theory and the experiment, and this is due to they have different second sound velocity. To get more accurate results, this is in the future, so we would like also to apply boundaries for full linearized PTE to get more accurate results. Finally, thank you for taking the time to listen to me today, and thank you very much for your attention.